So we left with a very small this thing over here, topic of coordinate chemistry, which we are going to do today and finish with this and start with organic, right? So now हम लोगों ने पिछली वाली क्लास पे क्या किया था? हमने किया क्रिस्टल फील्ड थ्योरी CFT, ओके? और CFT के बेसिस पे हमने जो D ब्लॉक है उसको हमने डिवाइड किया into two. One was T2G and the EG orbitals. T2G they were at a lower energy level and EG they were at a high energy level. Now this particular concept, that is the splitting up of orbitals on approachment of the ligands towards the central metal atom, ये बहुत सारी properties जो है coordinate compounds की explain करता है. जैसे magnetic behavior explain करेगा, ये color भी जो है that it will explain on the basis of the transitions which are going to take place, the DD transitions, उसके basis पे ये color भी explain करता है. So let's go on to the first property which we are going to discuss today, that is the magnetic nature of coordinate complexes. Magnetic nature of coordinate complexes. Now when we are talking of magnetic nature, we already know that substances which have unpaired electrons or which have a magnetic moment such substances they are going to be attracted by the magnetic field, and such substances they are going to be known as paramagnetic in nature. Okay, this we have done when we were doing the D block. We've done this topic already. So because here पे D block they are going to be the central metal atoms. So all those central metal atoms, D orbitals which are having unpaired electrons or magnetic moment, they are going to be paramagnetic in nature. ठीक है? फिर उसके बाद all those which have paired electron and they have zero magnetic moment, all those they are going to be diamagnetic in nature. Now diamagnetic का मतलब क्या हुआ? Diamagnetic means over here that they are going to be repelled by a magnetic field. The spin due to one that is going to be cancelled due to spin of the other, right? So this we've done quite in detail when we were doing the D block. And we also know that the Bohr magnetron, that is going to be the property which measures the magnetic moment and which is denoted by nu, right? This nu that can be calculated as n into n plus 2, where n that is going to be equal to number of unpaired electrons which are present. So greater the number of unpaired electrons, greater is going to be the value of mu and greater is going to be the paramagnetic nature. तो इससे आपको क्वेश्चन कैसा आता है? Which of the following is most paramagnetic? So they have given you Cr3 positive, Fe3 positive, CO3 positive and Ni2 positive. So how will you find out? In this you have to see the electronic configuration. In case of here 3D क्या कहते हैं इसको, Cr3 positive, the electronic configuration will become how much? It will become equal to 3D3. Chromium has 3D5 4s1. So अगर 3 उसमें से निकल गए तो 3D3. When we go to Fe3 positive, so Fe की electronic configuration क्या हुई? 3D6 4s2. So that means this is going to have 3D5 electronic configuration. When you go to cobalt की electronic configuration कितनी होती है? 3D7 4s2, right? So 3D7 4s2 means this is going to have 3D6 and nickel 2 positive electronic configuration is going to be 3D8 4s2. So this is 3D8. Now when you're looking over here, this has 3 unpaired electrons, this has 5 unpaired electrons, this has 4 unpaired electrons, and this is going to have how many? 5, 6, 7, 8. Only 1 unpaired electron, right? So क्योंकि number of unpaired electron arrange करना है आपको in order of increasing मैग्नेटिक या पैरामैग्नेटिक कैरेक्टर, तो सबसे कम फिर किसका आएगा? Ni2 पॉजिटिव इज गोइंग टू बी लीस्ट. उसके बाद वी विल हैव CO3 पॉजिटिव, उसके बाद वी विल हैव Cr3 पॉजिटिव एंड देन फाइनली वी आर गोइंग टू हैव Fe3 पॉजिटिव. Got it? So this is the increasing order of paramagnetic character depending upon the number of unpaired electrons which are going to be present. So this is what magnetic property is and the reason of magnetic property. The second property which we are going to do over here is color. Now when we are doing the color of any organic compound coordinate compounds, the color that is going to be due to DD transitions. Now we can explain this by taking the example of titanium H2O pole 6 3 positive. Okay, now you know over here that titanium 3 positive का मतलब क्या हुआ? Titanium की electronic configuration क्या है? It is going to be क्या होगी? 3d2 4s1. This is going to be the electronic configuration, right? Now if in case over here we are taking titanium 3 positive, so how many d electrons are going to be there? 0. They are going to be 0 d electrons, right? But if we are talking of titanium that is going to have how many d electrons over here? 2 d electrons, isn't it? If you are talking of titanium over here, the electronic configuration that is going to be 3d2 4s1. So it has 2 d electrons. Okay. Now in this case what happens is when we are talking of titanium over here, these 2 electrons they can jump from a lower energy level to a higher energy level. The lower energy level is going to be T2G and the higher energy level that is going to be Eg. So the 2 electrons they can jump from the lower energy level by absorbing light and going to a higher energy level. Now what really happens is the source of light, if we are taking sunlight as the source of light, that is white light. Now if any substance that is going to absorb the entire white light, all the wavelengths of the white light, it is going to appear black. But if it is absorbing light of certain wavelength, it is going to emit light of the other wavelength. तो हमें जो color नजर आता है, that is going to be the emitted light, not the absorbed wavelength. Okay. Now we already know that if you are talking of energy over here, energy that is equal to hc upon lambda. ठीक है? Or in other words, we are saying over here, h is a constant, c is a constant. So energy that is going to be inversely proportional to lambda. Right? Now let's say if we have any molecule or any coordinate complex which has higher energy. Now energy over here we are talking of what in terms of crystal field splitting energy. If the crystal field splitting energy that is going to be higher, what happens? It is going to absorb wavelength of, or it is going to absorb radiation of low wavelength. ठीक है? So अगर एक कोई भी कोऑर्डिनेट कॉम्प्लेक्स की क्रिस्टल फील्ड स्प्लिटिंग एनर्जी ज्यादा है तो वो लो वेवलेंथ वाली एनर्जी को एब्जॉर्ब करेगा, और अगर वो लो वेवलेंथ वाली एनर्जी को एब्जॉर्ब करता है तो इट इज गोइंग टू इमिट रेडिएशन ऑफ हायर वेवलेंथ. ठीक है? इफ it is causing more energy, obviously it will emit radiations in the lower energy, and lower energy that is equal to what? Higher wavelength. ठीक है? So on the basis of this, there is one complementary or a color wheel which has been designed in order to tell us the radiations which are absorbed and the radiations which are going to be emitted. So let's see what is this color wheel all about. Okay, so we are saying over here there is a color wheel which has been designed which shows that any radiation, if any coordinate complex that is absorbing radiation of higher wavelength, it is going to emit radiation of lower wavelength. ठीक है? Now let's see that above this is 800 nanometers, and below this is 400 nanometers. And you also know that the visible radiation that is in between 400 to 750 nanometers. ठीक है? And this over here is going to be 560. So we have VIBGYOR. Okay, where violet that is going to have the least wavelength and red that is going to have the highest wavelength. Okay. Now anything which is going to absorb red, it is going to emit over here green. So red and green, they are said to be complementary colors of each other. If any compound that is absorbing green, it will appear red, and any compound which is absorbing red, it is going to appear green. Okay. Now over here, if 400 nanometers, that is going to be violet. Okay, so violet अगर वो करता है, तो it is going to appear yellow. Therefore, violet and yellow, they are going to be again complementary colors of each other. ठीक है? Similarly, orange, and the complementary color of orange, that is going to be blue. Okay, so we're talking of complex which has क्या बोलते हैं उसको D1, right? Any complex which is going to have D1 over here. So D1 complex means that the one electron that is going to be at a lower energy level. ठीक है? Now it is going to absorb radiation, HU light. Right? Now when it is absorbing radiation, this will get excited to a higher energy level. Okay, so if it is having a higher energy level, when it will come back to the ground level, it is going to emit radiations. Right? So when it emits radiations over here, then what is going to happen? If it is emitting radiations, it will emit radiations in the UV light, and hence it appears colored. Now over here we have committed a mistake. The electronic configuration is going to be 3d24s1. So titanium in the 3 positive state, when we are looking at titanium in the 3 positive state, the electronic configuration that is going to be 3d1. So it has one electron. So ये जो आपके पास यहाँ पे हम show कर रहे हैं, this can be shown for titanium H2O6 3 positive. It has one electron. It is going to absorb energy and go to a higher energy level, and when it comes down, it is going to give us radiations. ठीक है? Clear हो गया? Now on the basis of this, when we are taking an example of a complex ion, let's see what is the wavelength it is absorbing and what it is emitting. Over here we are taking coordinate complexes of cobalt with different ligands. Okay, you will see that the weak field ligands, जैसे COF6, we know that fluorine, that is a weak field ligand. In case of weak field ligand, the energy, crystal field energy, that is going to be less. So if the crystal field energy is going to be less, it is going to absorb radiations of higher wavelength, because energy is inversely proportional. So over here it is seen that COF6 that absorbs energy of 700 nanometers. So it is absorbing energy of 700 nanometers. It means that it is absorbing the red radiation or the red color from the VIBGYOR. ठीक है? और अगर वो red करेगा तो उसको क्या appear होना चाहिए? It should appear green. So this COF6 appears green. It absorbs red and it appears green. ठीक है? Then we are going to a little stronger ligand in this. We are taking the oxalate ion over here. So we have CO, C2O4 whole thrice 3 negative. Again, although this is a weak field ligand, but it is stronger than fluorine. So you will see that it will absorb radiation of a little lower wavelength, 600 nanometers. So 600 nanometers is yellow. Now if it is absorbing yellow, it should appear to us as violet. ठीक है? So पर वो बिल्कुल violet नहीं होता है. It appears to us as a darker green and blue color, which is equivalent to violet only. So you can write violet over here. But otherwise in the books it is given books it is given dark green. Okay. Then next we are taking, again let's say we are taking a strong ligand now over here, we are taking ammonia. Now NH3 is going to have a high crystal field splitting, so we will see that it is going to absorb wavelength of less, or absorb radiation of less wavelength, which is going to be blue, 475 nanometers. So when it is blue, it is going to appear orange. ठीक है? So जितना हम ज़्यादा strong ये लेते रहेंगे, ligand लेते रहेंगे, उतनी ही जो wavelength होगी वो कम होती चली जाएगी. जैसे अगर हम लोग साइनो ले लेते हैं, साइनो is going to be one of the strongest. COCN6 3 negative. Cyano, that is one of the strongest. So it is going to absorb radiation of very less wavelength, approximately of the order of 310 nanometers only. So 310 nanometers is even lesser than 400. So it will go to the UV radiation. It is going to absorb UV radiation, and this appears to us as very pale yellow. Have you understood the concept over here? Greater the crystal field splitting energy, lesser wavelength absorbed, and according to that, the color that is going to be predicted. Right? So let's go on to the next topic, the second last topic of this chapter, that is stability of coordination compounds. Okay, now when we are talking of stability of coordination compounds, the coordination compounds की stability that is going to depend upon one important factor which is known as the stability constant. So when we are going to stability of coordination compounds, we can say that any coordination compound की जो formation होती है, that will depend upon the fact how easily a ligand is approaching the central metal atom and how easily is it forming bonds. Okay. Now if in case we want to form one complex of the type Ml4, this complex formation is going to take place in 4 different steps. In the first step, one ligand that is going to approach to give us Ml. So if you're talking of the stability constant which is given by K1 for this particular reaction, that will be given as concentration of Ml upon concentration of M into concentration of L. Okay? Now in the second one we have Ml, then another ligand that is going to approach such that we will now have Ml2. And what is going to be the value of K2 over here? It is going to be Ml2 upon concentration of Ml into concentration of L. Okay? Then in the third step, Ml2 will again coordinate with another ligand to give us Ml3, such that K3 over here now becomes concentration of Ml3 upon concentration of Ml2 into concentration of L. Okay? Then we come to the last step, Ml3, one more ligand that is going to approach, we are going to get over here Ml4. And what is going to be K4? It is going to be Ml4 upon concentration of Ml3 into concentration of L. So it means when we are talking of the total stability constant over here, Ks, that is going to depend upon all the stability constants. Over here the value of K1 that is going to be the highest and the value of K4 that is going to be lowest. But if the total stability constant has to be calculated, it will be equal to K1 into K2 into K3 into K4. Right? So higher the value of overall stability constant over here, more stable that is going to be the compound. Now, if we are taking reverse reactions over here, that is, we are dissociating the coordinate complexes back into the ligands and the metal ions, then that is known as dissociation constant also known as instability constant. The instability constant that is given by 1 upon K. Okay, so what do we have over here? It means that greater the value of stability constant, greater is going to be the stability, but if greater the value of dissociation constant, lesser is going to be the stability, because they are reciprocal terms of each other. Okay? Greater the stability constant, greater is going to be the stability, and lesser the stability constant, greater the dissociation constant, lesser is going to be the stability. Okay? Now let's go on to factors which are affecting the stability of the complex. The first is nature of the central ion. When we are going to factors over here, the first one that is going to be the nature of central metal ion. Right? When we are looking at the nature of the central metal ion, it is seen greater the charge, greater is going to be the stability. So the first one is greater the charge. This is important for you for your competitions, okay? Greater the charge, greater is the stability. Okay, so if we are having complexes of Fe2 positive and Fe3 positive, the complexes of Fe3 positive, they are going to be stable. Right? Second, it will depend upon the size of the central metal ion. Size of the central metal ion. Now, size of the central metal ion, it is seen that as the size decreases, the stability will increase. So, we are saying that as size decreases, stability that is going to increase. Like for example, let's take the sizes of the few cations over here. We have Mn2 positive, which has a size of 91 picometers. Then we have Fe2 positive, which has a size of 83 picometers. Then we have CO2 positive, 82 picometers. And then we have Ni2 positive. Ni2 positive has a size of 78, and then we have CO2 positive, which has 69, and then we have Zn2 positive, 64. Okay? Now over here, as this size is going to decrease, the stability will increase. So the stability increases in this order. And this order that is known as Williams order of stability. Okay? So these are going to be the factors which are going to affect the stability of the ions. Now this is, we have only taken into account what we are taking into account, the central metal ion. So let's go on to the ligands over here. Now when we are talking of ligands, it is seen that in case of ligands, the cyno, let's say that we are taking the ligands now over here. In this case it is seen, number one, the cyno and NH3. Cyno and amine, they are going to be far more stable than those of halide ions. So it means that the strong field ligands, they are going to form stable coordinate complexes. Okay? For number two, the chelating ligands. Chelating ligand means bidentate, tridentate, tetradentate and hexadentate. They form more stable complexes. So in this case, hexa is going to form the most stable. फिर उसके बाद penta, tetra, tri and di. So this is how the stability that will decrease with respect to monodentate. ठीक है? Then number 3, all those which are going to form cyclic compounds. They are going to be more stable. All those which form cyclic compounds, they are going to be more stable. ठीक है? Now metals over here, when we were doing the metals, so in case of metals, the metals they have been classified into 3 categories with respect to their ease with which they can form the coordinate complexes, and hence क्या कहते हैं how the stability that is going to increase. जितना easily it is going to form the bond, उतना ही ज़्यादा is going to be the stability. Okay, so according to that, we have over here the metals. They are classified as, we know that all the metals they are going to be acceptors. So we classify the metals into the following categories, and all the metals they are going to be Lewis acids. So we say that number 1, metals they are going to be acceptors. Number 2, they all are going to behave as Lewis acids. ठीक है? So these are the 2 important this thing of metals. Now let's see that on the basis of their acceptance power, we classify the metals into class A metals. Class A metals, they are all going to be known as hard acids. ठीक है? So generally the metals of group 1 and 2, that is alkali metals and alkaline earth metals, they are going to come under this category, and the inner transition metals, ठीक है, that is inner transition metals from group 3 to 6, all of these they are going to be highly electropositive in nature. Okay, so group 3 to 6 transition metals, they are also going to come under this category. They are going to form stable coordinate, the most stable coordinate complexes you can say. ठीक है? Second और पास आ जाता है class B. Class B they are known as soft acids. Okay, so these are going to be less electropositive and they consist of heavy metals. Heavy metals of the type rhodium, palladium, silver, iridium, platinum, gold. So all these heavy metals they are going to come under this category. Then we have class C. Class C they are borderline metals. Okay, they have certain characteristics of metals. For example, we have manganese, we have nickel, copper, iron. All these they are going to form, even for that matter cobalt, they are the borderline metals. ठीक है? So these are going to form the most stable compounds, then these and then the C ones. So this is what stability is. Then the last topic which we are going to do, that is metal carbonyls. So let's understand what metal carbonyls are. Okay, so when we're talking of metal carbonyls. Metal carbonyls are those coordinate complexes in which carbon monoxide behaves as a ligand. So these are more commonly known as carbonyl complexes, or because all the ligands they are going to be same, they are also known as homoleptic carbonyls. Okay? They are also known as homoleptic carbonyls. When we are talking of structure of metal carbonyls, they have the same structures as a general, you can say, coordination polyhedra. For example, if we are taking nickel carbonyl, this is going to have a tetrahedral structure. So we have nickel, carbonyl, this and this. So this is going to have a normal tetrahedral structure. If we have FeCO5, this is going to have trigonal bipyramidal geometry. So we have over here FeCO. This has a trigonal bipyramidal geometry. And if we have chromium, this is going to have a octahedral geometry. So we have chromium, CO, and CO. Okay? So this is octahedral geometry over here. Okay, but there may be certain bridging compounds also present. For example, we have Mn2CO10. Now over here, both the manganese, they are going to be bonded to one another. So it is going to have 10 carbonyl groups which are going to be arranged. So 10 carbonyl groups means we have, how many we made? 6. है ना? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 बन गए. Okay, so this is going to be Mn2CO10. So this has a bridging manganese in this. The most characteristic property of the carbonyl compounds is going to be its bonding. It has a special kind of bonding which is known as the back bonding, right? Now how does this bonding arise? Let's just see, let's make a molecular orbital picture of carbonyl first, carbon monoxide. Okay, so if you're taking a picture of carbon monoxide means one carbon and one oxygen. Okay, so in case we have over here, let's see that this is the molecule 2s and 2p for carbon, and this is 2s and 2p for oxygen. When you're looking at the electronic configuration, it is going to be 2s2, 2p2, okay? And over here it is 2s2, 2p4, right? So when we are drawing the orbital picture over here, it is going to have sigma 2s, sigma anti-bonding 2s, ठीक है? फिर उसके बाद यहाँ पे हमारे पास बनेगा this is going to be there. So we have over here sigma, pi 2px, pi 2px, pi 2py and sigma 2pz, pi anti-bonding 2px, pi anti-bonding 2py and sigma anti-bonding 2pz. So now when we have to fill up the electrons, 4 electrons will come here, 1, 2, 3 and 4. ठीक है, और यहाँ पे हमको 1 2 3 4 5 6 भरने हैं, so we have 1 2 3 4 5 and 6, right? Now when you're looking at the most highly occupied molecular orbital over here, that is going to be sigma 2pz, right? Now the ligand that is going to the metal that is going to donate these electrons to the ligands, right? And when we are looking at the most unoccupied, most you can say highly energy wala unoccupied, वो कौन सा होगा? That is going to be pi over here. So there are two types of bonds which are formed over here. The first one, that is the sigma bond, right? This sigma bond that is going to be formed between the metal and the ligand. That means the ligand that is going to give electrons to the metal, which is a normal kind of this thing bond, which is generally the dative bond which is formed. The ligand, it is giving electrons to the empty orbitals over here, so that is going to be one bond which is formed, right? So you can write down in this, in the first point, there is a donation of lone pair of electrons of carbon in the suitable empty orbital, in the suitable empty orbital of the metal atom. To form a sigma bond, and the normal dative bond formed in coordinate complexes. Normal sigma bond formed in coordinate complexes. Then number 2, there is a pi overlapping of donation of electrons from filled metal d orbitals into vacant anti-bonding pi. So these are the vacant anti-bonding pi which are present over here. This is going to form a pi bond from the metal to the ligand. This is known as back bonding, which stabilizes the structure of metal carbonyls. ठीक है? So with this we finish our coordinate chemistry. The next chapter which we will start, that is chapter 10, haloalkanes. The second book is not going to take a lot of time because we only have a lot of reactions in that and we don't have any numericals. Okay? So second book we will finish faster.